Hello, good morning. My name is Gajraj Kuldeep, and I'll talk about my PhD project at Secure Data Compression for Internet of Things. And in this talk, I'll briefly explain what is my project and what work I'm doing. So first of all, why this project? As my project's title suggests, that Secure Data Compression for IoT. So basically, I'm working in Internet of Things, and there are right now, if we talk 2021, it's 46 billion devices approximately. And these many devices, and some of them are resource constrained, and they generate enormous data. And the communication channel, which is going to be harsh because the most of the resource constrained device going to work in the ISM band, that's the 2.4 or 2.5 gigahertz, and the next ISM band. So the communication channel will also be very harsh. And the data generated should require some kind of secrecy. So here I'm catering for data compression, error correction, and information secrecy. So for this, conventional solutions are for data compression, one can use transform coding and entropy coding like Huffman and many other like arithmetic. And for error recovery, one can use RS, PCS, and LDPC codes. And for encryption, also AES is most widely used encryption algorithm. But why do we need a new thing when we already have state of the art? Because the devices which I'm working are they are very resource constrained and they are battery operated. So most of the algorithms they cannot be implemented either, and if they are implementable in these devices, they are not energy efficient. So the goal of my project is to provide end-to-end information secrecy, data transmission and storage secrecy, and energy. These all operations should be energy efficient. And how I'm going to do this is basically I'm trying to merge all the three, like compression, error recovery, and information secrecy in a simple matrix vector to achieve all the three tasks in energy efficient way. So for completing that task, I'm using compressive sensing, that is a signal processing technique, which basically is a matrix vector multiplication. So we have a vector. So I'm working on natural signals. So they are sparse in some transform domain, which is the constraint on this scheme. So we take a matrix vector multiplication, and then we get another vector which has a less dimension. So basically we achieve compression. And for this kind of system, if we change the sensing matrix, one can understand this as a Hill cipher. Every time one changes the sensing matrix, then get the ciphertext. In cryptographic terms, Xi is a plaintext and Yi is a ciphertext. So by default, it reduces the dimension from N to M, and the mutual information between plaintext and ciphertext is given as mutual information of the energy of the signal and the Yi. So this equation 1 tells us that one can only learn energy of the input signal if we do all this kind of linear encoding. And the recovery is using the L1 optimization. So the signal is sparse in phi. One can apply the L1 minimization and recover the signal. So in the first task, I studied the existing CS-based encryption scheme. So I asked how well does the compressive sensing in general setting provide security, and what kind of attacks are possible on the state of art. So from this equation, we know that, okay, it can leak energy. So I designed a decoding algorithm which exploits the correlation among signal blocks. And I also performed statistical analysis for different kind of sensing metrics. And I applied cryptanalysis attack. That's a ciphertext only attack on one of the scheme. And this is the power signal. So this is the reconstructed signal from the ciphertext. One can easily see that it leaks the power profile. It doesn't recover the exact signal, but it where the changes are there in the signal, it recovers my designed decoding algorithm actually recovers the signal. Then I proposed energy concealment scheme. So basically, we see that compressive sensing measurements leaks only energy. So I defined a transformation which sends a vector to another vector space, that's the sphere surface of n+1 dimension, such that the energy of the new vector is Emax. So one can easily decide the maximum energy to be 2 raised to the power of 32 or 2 raised to the power of 64 based on the processor. And the mutual information in this case will be like I between the plaintext and ciphertext will be Emax and YI. So from this, the adversary will not be able to recover anything because he will just always get the Emax, which one can always make it public. So in this scheme, basically, I first add energy concealing variable, then perform the compressive sensing, then transmit through an insecure channel, then at the recover side, apply a optimization algorithm, and then remove the energy concealing variable and get the plain text. And this is the prototype of energy concealment scheme. So I implemented in TLSP mode and using quantity NC. So RAM is 10 KB and it's a highly constrained device, resource constrained device. And in this, like the A is from the AES, and here T is the encryption time, and this is the transmission time. But my scheme performs both the operations, like it compress in one operation and provide confidentiality also. So it takes, it reduces the transmission power as well as the encryption time. So AES take around 100 milliseconds to encrypt a plain text of block size of 256 bytes in my case in this device. I also applied Cyphertext Static on various state-of-art schemes. So here, this is one image, and one can see that if from one-time sensing, I'm able to recover the plain text information. Similarly, there was another scheme, energy obfuscation scheme. I was also able to recover plain text information, but for my scheme, the attack was not applicable. Then I also introduced a multi-class privacy-preserving scheme. So in this, there is encryption at the sensor node, but there are two parties which can get different information based on their keys. So if this is the example of statistical decryption, so there are like super user who recover the complete signal, but semi-authorized user can only statistical information like mean, variance, or other histogram of the signal, but not the plain text value, exact values. And the cloud will not recover anything. And similarly, this is the example for data anonymization, and the face is for this application. I'm calling suppose face is a sensitive region. So for semi-authorized user, the face is not detectable, whereas for the super user it is. Then the third scheme which I propose is able to combine all four functions, but because I don't have hardware, so I'm working on right now compression, encryption, FEC. Incrust can perform all the scheme which I propose. I call them Incrust. That's error robust compression and encryption scheme. And this achieves like compression error recovery. It achieves information secrecy, and the complexity is just a matrix vector multiplication. So yeah, so if we have like here, just we need to require two matrices A and B, and these matrices can be pre-computed, and then only one matrix vector multiplication is required. So it recovers error as well as compress, and it provides information secrecy. So here is an example of error robustness. Just go for the image. Yeah. So these A and C are the reconstructed image from the AES, and B and D are reconstructed images from the encrust. And I also use RS for the AES. That's the standard case. So RS code for error recovery. And here it can see that error robustness in my case, the image is perfectly recoverable. But if there are errors in this, then this is not the case with the AES. So it's for AES, the sharp fall in the performance, whereas for the encrust, the fall is graceful. And these are my research outcome. So like I already published 3 papers in conference and 1 in journal, and 2 are under review. And now with this, I end my talk, and I'll be happy to answer some of them.